Unit prices for foundation model APIs are dropping steadily across the industry. Yet, at the exact same time, enterprise compute bills for agentic-AI workloads are exploding. This happens because engineering teams follow an industry default trajectory known as token maxing. When an agent needs a capability boost, developers buy that marginal capability by submitting monotonically increasing token volumes to the foundation model. Architecturally, this manifests as longer reasoning traces, higher iteration caps on conversational turns, and thick context windows that are replayed in full, over and over. This chart visualizes the Jevons dynamic. Unit token prices trend down, while total enterprise API spend curves aggressively up. Efficiency gains simply finance token maxing. Teams treat tokens as free at the margin, raising total consumption and masking architectural bloat. You will not see this bloat in benchmark tables. Those evaluations exclusively report task quality. You will, however, see it plainly on your massive cloud invoices. If an engineering organization defines agentic progress purely by capability benchmarks, their total spend will continue to rise, regardless of how cheap the underlying API becomes. When the invoice gets too high, teams default to a standard set of fixes. They aggressively prune their system prompts, they wait for the next price drop from the provider, or they switch to a smaller, cheaper foundation model. They assume the foundation model dictates the bill. It doesn't. In the one-time stack, spend is generated one layer up, in the harness. This orchestration software handles context assembly, exposes tool schemas, sequences turns, manages memory, and executes retries. A 2026 paper by Syed Ali and researchers at Writer isolates this layer. Their thesis is direct. The harness controls nearly every term of the token bill, along with the effective price of the most dominant input tokens. Escaping the token maxing trap requires solving a software architecture problem, not a model selection problem. The harness is the actual P&L of an agent system. An agentic task is never a single isolated API call. It's a loop of k turns. The financial bill for a completed task is the sum over that entire loop. Turn inputs break down into 5 variables: system prompt, history, tool schemas, retrieval, and the user turn. The orchestration software assembles 4 of the 5, and the user turn is external. The harness also governs the retries that multiply this equation. A naive agent architecture handles this loop by replaying the full, unedited transcript on every single turn of the task. Naive replay scales input tokens quadratically due to history replay. The system prompt, schemas, and retrieval remain linear. By applying structured compaction, folding older history into bounded checkpoints at 80% of the input limit, a harness flattens that curve to linear. Bounding the history term drastically cuts the token volume. We achieve this entirely in the orchestration layer, without altering a weight in the foundation model. Production agent workloads run at an extreme input-to-output token ratio, consistently sitting near 100:1. Because output tokens are a negligible fraction of the volume, the input price dictates the entire financial bill. This introduces the economics of prompt caching. When an API provider serves tokens from a cache read, meaning they recognize a prompt prefix they've already processed, they discount those tokens to roughly 10% of their base rate. This equation models the effective input price under a caching system. The variable kappa represents the provider discount, about 0.1. The crucial variable is h, the fraction of your input tokens served as cache reads. The industry broadly misunderstands h. It is neither a capability of the model nor a favor granted by the provider. It is entirely a function of prompt byte stability across turns. The harness controls byte stability through a 2-zone prompt. The massive byte-stable prefix holds tool schemas, the system prompt, and transcript, locking into the provider's cache. The tiny volatile tail holds clock data and plan states, rebuilt locally on every turn. When you enforce this cache shape as a strict architectural rule, the math shifts. The researchers measured an identical prefix call where 99.9% of the prompt tokens registered as cache reads. The orchestration layer wields a double lever. Compaction dictates how many tokens are sent, while cache shape discipline slashes their price by 90%. The researchers proved this math empirically with a controlled swap. They locked 22 enterprise tasks, used identical judges, and applied a static price table across 6 different foundation models from 5 vendors. The only variable they changed was the software. They swapped a naive conventional agent loop for a highly structured harness. The blended baseline results held task quality perfectly flat while reducing tokens by 38%, dropping latency by 44%, and cutting the total cost per task by 41%. This chart shows the critical signature, model invariant efficiency. Every single model got 33 to 61% cheaper to run. There were 0 exceptions across 5 vendors and 3 distinct weight classes. This uniformity proves the savings are a pure layer-level effect. Now, the scatter plot for quality gains. The correlation between a model's baseline strength and its quality gain sits at 0.99, harness leverage. Strong models convert the rigid orchestration structure into a measurable quality boost. Weaker models simply experience it as load. The harness guarantees an unconditional economic floor. Every model gets cheaper to operate, but the foundation model strictly sets the quality ceiling. This exposes why orchestration IP is strategically more valuable than model selection in a multi-agent fleet. If you optimize a single foundation model, you only improve one specific cost variable in your stack. If you improve your routing logic, you only optimize the usage mix. A harness optimization acts as a mathematical multiplier, simultaneously compressing the operating cost of every model in your fleet. Because the harness sits above the API, this multiplier remains intact even when swapping foundation models. The orchestration layer is entirely indifferent to which vendor wins. That today, there is still a massive managerial hurdle. If engineering teams are only judged on capability benchmarks at release, they will inevitably return to token maxing to hit their targets. The operational fix elevates a new metric to the release gate, CPM, or completions per million tokens. You evaluate token intensity exactly alongside task quality. We track performance per watt in chip design because raw speed is absolutely useless if it completely melts the server. Escaping the token trap requires the exact same discipline. Measure efficiency alongside capability and treat the harness for what it is, the true P&L of the agent system.